Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening, I'm Yvonne Stapp for Science for the Public, and welcome to our lecture series tonight at the Robbins Library in Arlington. And tonight we are very honored to present Tulika Bose, Associate Professor of Physics at Boston University. Dr. Bose is the trigger coordinator for the Compact Muon Solenoid, the CMS, project or experiment at the Large Hadron Collider at CERN. She'll explain all that tonight. In this presentation, she brings the most recent news, and I'm not kidding, she's just here from there briefly, and an explanation of what scientists are looking for this time around. Tulika Bose received her Ph.D. in experimental high-energy physics from Columbia University in 2006. She did postdoctoral work at Brown University, but her work has been in these kind of exotic particles, so I hope she'll say something about that tonight. She's been involved in a number of very interesting projects, including the CMS project at CERN. She's worked extensively on trigger and data acquisition in all of these projects as well. She's the author of numerous publications and is actively involved in searches for new physics using the data collected at the CMS. After a 2-year shutdown at the Large Hadron Collider to make the adjustments to practically double the collision energy, the 215 run has begun, and physicists are looking at new data at an unprecedented collision energy of 13 teravolts, almost double the energy of the previous 2010-2012 run. And that run produced all the news about the Higgs boson, what they found, the discovery of the Higgs boson. And this time, they're anticipating entirely new discoveries, and you can ask her all about that tonight. We are very grateful for Dr. Bose providing this update, since she's spending just a brief time here in Boston before she goes back to CERN. Please welcome Dr. Tulika Bose.
Thank you very much, Yvonne. It's a pleasure to be here today to talk to you all. So what I'll talk to you about today is unlocking what I call the secrets of the universe at the Large Hadron Collider, or in other words, what's recently happening there. Now, firstly, to begin with, what is the Large Hadron Collider, or as we call it, the LHC in short? Large in this case is really an understatement, and you'll see more about this later. Hadrons, the second word here, refers to what are called protons, and I'll talk more about this as well. And collide is what we do there, and again, you'll see more about this. So what is it that we do at the Large Hadron Collider at CERN? Back, maybe in the early 20th century, these were probably how, you did experiments. Get ready with two things that you just throw at each other and see what comes out. The world today, collider physics, is very different. But to sort of motivate what it is and why do we want large energies to get to what we want, I have an analogy here for you. This is an illustration supposed to show two helicopters, and you should look at the bar at the bottom, which is giving you an idea of what the energy in this particular accelerator is, where you're going to try and collide these two. So the question is, if these two come and collide, what do you expect to see? An explosion, exactly. So let's try to make that happen. And indeed, that's what you see. You have all of these particles that come out. So what it's saying is that these helicopters are what are called composite objects, meaning they're composed of different things, and you see the little bits that are thrown about. So now let's go next step up. you see it's the same picture, but now if you look at the bottom, the accelerator energy is larger. So I've put in more energy into the accelerator, so they're going to come faster, and then they're going to collide. And then what do you expect to see after this collision? A bigger explosion, and as a result of the bigger explosion, the particles that you see come out of it, will they be bigger or will they be smaller? Smaller, exactly. So this is exactly your common intuitive sense is correct, and indeed what you see is smaller pieces come out of this more energetic collision. And doing experiments like this has allowed us to see sort of smaller and smaller particles over the course of the year, not necessarily all through collisions, but the idea is the same. So we've gone from, when we knew about the molecule as being the, an elementary sort of particle, to understanding that no, a molecule, consists of atoms. And then moreover, an atom has, an inner nucleus, and surrounding it you have these electrons, which you see on the extreme right there, and they are elementary, meaning we haven't been able to break an electron down into anything smaller. And this is what particle physicists call elementary, and the kind of particles like the electron are called leptons. It comes from a Greek word which means light. So they're extremely light, almost massless particles, so we call them leptons. Now, we then further went ahead and started, looking inside the atom, and then we found that in there, essentially, at the inner part of it is the nucleus. And the nucleus is also not elementary, but rather is composed of other particles. And these, we find, are called the proton and the neutron, which in the particle physics world, we call them hadrons. Again, this is Greek, meaning heavy. So in comparison to the leptons, like the electron, which are light, these hadrons in comparison are heavier, and hence the name. Then we went further, and we found that these protons and neutrons are not elementary as well, but rather they can be broken down into still smaller constituent particles. And in this particular case, the particles composing the proton and neutron are what are called quarks, and in particular two kinds of quarks, up and down quarks. The name doesn't mean anything. It doesn't mean that one of them lives up and the other one means down. These are just names that particle physicists come up with, and sometimes the names are crazy, but that's what they are. What I call these up and down quarks are similar to what you think of as Lego bricks. I have a 5-year-old who loves playing with Legos, and so this is like a little brick of up and a little brick with down. And what we will have is that you have put in the lepton, and that is the electron that I've talked about. But now you can make different combinations of these quarks to yield the hadron that we were talking about. And this is the answer to your question, that if you look at the proton, it's composed of 2 up quarks and a down quark, while the neutron is composed of 1 up quark and 2 down quarks. So they're composed of the same quarks, but in different numbers, and that results in making them different. And so this is starting with sort of the minimalistic Lego block, and from that you have created a proton and a neutron, and the other brick is your lepton. So what do we do next? Well, we can go with this. We'll try to build an atom now. So we have something that we are going to build with 2 protons that you see on the left and 2 neutrons that you see on the right. And if you put these Lego bricks together, can anybody say what you create? Helium. Very good. This is helium. So now you can essentially take this, and of course you need your electrons, and your electrons are going to be whizzing around, and you got your helium atom. And what you do next is you take this and you multiply it by billions and billions and billions of other such permutations and combinations, and essentially that's what results in the universe that we know. What we can observe, it's composed of all of these various quarks and leptons in different combinations. But that is not the end of the story. What we now get to is another case of the 2 helicopters in my analogy coming to collide. Now the accelerator energy is even higher. Okay, we've reached the maximal point. So again, I will ask you, they're going to collide, and what do you expect to see? Yes?
When the particles break.
Yes, so that's what you think, that you would, again, you've created particles, and these particles in turn will break into further smaller particles. So you've sort of moved ahead, but what we are going to see is the same thing happening here. Now, in this collision, I created two dinosaurs. In reality, that's not what we do at the LHC. However, there is a connection. Dinosaurs, we say, from the Jurassic period, CERN is surrounded by these mountains called the Jura Mountains. And it was here that they found some of these prehistoric dinosaur bones. So the term Jurassic, as you know, comes from the Jura Mountains surrounding CERN. But that's a side note. We don't do any of dinosaur production at the LHC. But the main thing to highlight is what you saw was this collision yielded something completely surprising that you didn't expect. A particle which is, was there, but doesn't exist anymore. So what you did was you took the energy, and this energy of the collision was used to create these particles. And of course, what we will come to later is, what is it that we actually detect? Do we detect these dinosaurs in our experiment? And then we will answer the question that he already answered, that no, what we actually see is, well, the dinosaur decays into further, meaning the dinosaur doesn't live as a dinosaur, but instead splits up into still smaller particles. And our detector, we detect those smaller particles. But I'll come to that. So we've essentially taken the energy, produced special particles, and then we try and then look for these special particles that we have produced as a result of the energy. And the more energy we can put in, the more massive a particle we can hope to produce. So that's the reason why we want to go in for more and more energetic, higher energy accelerators, because then the probability of producing something bigger and more massive increases. Now, I just talked to you about, explained to you about the up and down quarks. However, those are not the only constituents, but rather, back at the beginning of the universe, you had a whole set of these, and this sort of comprises what is our known knowledge of the quark family. That is, you have your up and down, then charm and strange, top and bottom. I told you the names don't mean anything. It's not like it's a charming quark or this is a strange quark, but there were some historical reasons why they're named the way they are, but you just have to take them as they are. And then the leptons, the electron, its heavier version, the muon, and then the tau particle. And what are very special, at the bottom right, these very neutral particles. So the rest of them have charge. The quarks have charge, the leptons have charge, electric charge, while the ones at the bottom don't have charge. So they are neutral, as we see. And each of these is associated with a certain lepton. So the electron neutrino always goes together with the electron. The muon neutrino goes together with the muon, and a tau neutrino goes together with the tau. That means these are typically produced together in a particular process or reaction. So these are what we call our sort of our basic building blocks of the model that we particle physicists like to work with. But that's not the full picture, because there is also what's called the anti-version of these particles, or antimatter, or the fact that for every type of particle that we have, there is also an antiparticle. So just like there is an up, you're going to have an anti-up. There's a down quark, there's an anti-down. There were the other quarks, strange, sharp, top, bottom. They all have their anti-top, anti-bottom, anti-charm, anti-strange. And similarly for the leptons, you have your electron, and its oppositely charged particle is the positron. So the way a particle differs from an antiparticle is essentially through charge. It has the similar properties, but it is the opposite charge. There is a special category, and you will ask me, because I showed you about the neutral particle, the electron neutrino, and I show you here that it has its antiparticle, the anti-electron neutrino. And if you just heard me explain to you what an antiparticle is, I told you it has the opposite charge. So you're then going to ask me, but for a neutral particle, what does that mean? The main thing is that a neutrino is always associated with a lepton, meaning an electron neutrino is associated with an electron, a muon neutrino is associated with a muon neutrino. And its antiparticle is associated with the antilepton. So it is sort of linked to charge, even in spite of the fact that it doesn't have its own charge. And so there is a connection, and we call it conservation of lepton number or lepton charge. And so electron is always, comes together with its neutrino, and a positron comes together with its own neutrino, and that is the anti-neutrino. So together with the particles and the antiparticles, that sort of constitutes our knowledge of essentially elementary particles. And the neutrons and protons that we've mentioned, those are not elementary because they are broken down into these constituent quarks. They are what we call composite particles because they're composed of other things. Okay. Now, there is a very fundamental question associated with antimatter, and I will get to that more later. But it's the fact that, we, people, and everything we see around us is matter. At the very beginning, the Big Bang, we had, our current understanding tells us that we had equal amounts of matter and antimatter. And typically, when they will come together, they will annihilate. Somehow, something happened which resulted in all the antimatter going away somewhere, mostly, leaving all of us and matter behind. And what resulted in this, or what made this happen, we don't know. And that is one of the questions that the LHC and other experiments are trying to answer, is to understand what happened to the antimatter and why is everything predominantly matter. And I'll come back to, when I talk about what it is that we are actually looking at the LHC. So based on all of this, though I've already told you that there is, a lot of things that we now know. However, mostly I would say is we know actually very little. And that is because there are many, many fundamental questions that we still don't have an answer to. What we have an answer to are sort of the simple questions where, you take all of the information that I've given you, put it together in a model, and we particle physicists call it the standard model. It's nice and simple, and that sort of comprises our knowledge of the universe. However, there are, as I've already been sort of hinting, a number of mysteries and unknown answers, unknown questions, and I'll talk more about that. But before we get to that, I think it's useful to look at, together with these particles, the other big part of the standard model are what we call the fundamental forces, or how is it that these particles interact with each other. Now, these are sort of broadly grouped into sort of 4 categories, starting with the one on the extreme right, the electromagnetic force. This is the one that we sort of, experience most commonly in our day-to-day lives, what's responsible for, magnets, your TV working, etc. And that's a fundamental force. We say there is this particle called the photon, which is responsible for particles interacting via this electromagnetic force. There is what's on the left, the weak force, which essentially is explaining radioactivity, what powers the sun, the kind of interactions that power the sun. And there are these 3 fundamental particles, and they go by the name of W and Z bosons, and the W's have 2 charges, plus or minus, while the Z is neutral. And they sort of help the interaction of particles which sort of interact via this kind of a force, the weak force. And then there is a force called the strong force, which essentially is responsible for holding atoms together, for holding the quarks within the nucleus together. I mean, we talked about the up and down quarks. What we have is these are you can think of if you bring in too many similar type of charges, like if you have 2 protons within a nucleus. Why are these 2 protons, which have positively charged, and our knowledge of electrostatic tells us that if 2 charges are similar, they repel, while if they're opposite, they attract. So if you have two protons within a nucleus, you would expect them to repel each other and for the nucleus to break apart. However, there are various such nuclei existing, and they exist because there is this force, and that's why it's called a strong force, because it's able to overcome this other force there, the electromagnetic force, which was trying to repel them and to break it apart to keep it together. So there is this particle called the gluon, which literally is sort of gluing these quarks within it to sort of keep it together, and that is therefore responsible for the strong force. The Standard Model describes all of this beautifully. So these are the photon, W plus, W minus, Z, gluons, they're all particles. By now, we have discovered all of them. I think this was done in the 70s. The W and Z came about in the 80s. That was another Nobel Prize that was for the work done at CERN in the discovery. The force that the Standard Model does not know how to deal with is the force that we experience as we walk, as we go about in our everyday lives. Gravity, which is responsible for keeping us, well planted on Earth. And all the theorists in the world have not been able to fit in gravity in our current understanding of the Standard Model. So this, therefore, is very unsatisfying for everybody. Now, there are theories which try to do this, which, of course, we have no proof whether they are correct or not, but we are trying to figure out if indeed they are correct. And a majority of these theories say that just like there are these particles, the photons, the W and Z, and the gluon, which are responsible in a way for particles interacting via these forces, there must be a particle, and they call it the graviton, which would be then responsible for gravity, essentially, of particles interacting via gravity. So a lot of our searches at the LHC and other experiments are in sort of the hunt for the graviton. Because if you can find this graviton, you can then say that the theories which predicted it are therefore correct, and then we finally have an understanding of how gravity fits in within our Standard Model. So that's a fundamental, open, unknown question that we are trying to answer. That is, how can we get the Standard Model to include gravity? Then, the other big question that we have made some headway in understanding, but not completely, is the mystery of mass. So I think there was a question that I was asked as to, what are the masses of these particles? Are they all massive? This picture now has the same quarks and leptons, but now they are drawn on the basis of their mass, meaning the tiniest dots there are the least massive, and the bigger ones have more mass. So to sort of give you an idea of the mass of the particle. There is an empty space there. And does anybody remember what that quark was? Yes, very good. That was the top quark. And the reason I didn't have it here was if I tried to put it in here, its mass would make it sort of appear like this. It's a whole lot massive than the other particles. And there was, up until recently, we did not really fully understand why it is. So this was a big question, that is, why are some particles heavier than others, and what the Standard Model did not ever predict the masses of these particles. So we just went and did experiments to find them, and they had the mass that we discovered them at. But there was no prediction because it really couldn't tell us where mass for these particles came about. Okay, while some have mass, some particles like the neutrinos, for example, have very, very tiny mass. They're almost called massless. So then the big revolution came about in 1964 when there were 6 physicists working in sort of 3 groups. You had, from the left, Kibble, Guralnik, and Hagen. They were working together. Anglais and Braut working together, and Peter Higgs, who, in that same year, working independently, came up with 3 seminal papers that tried to answer the same question. And the way they addressed it or answered it was actually quite similar, with different, perhaps, take on things, but the basic idea or principle was the same. And they got published almost sequentially. There's a lot of debate about which came first, etc. But the bottom line is that all 3 of their papers came out in 1964. They all had the same mechanism for trying to explain how particles acquire mass. So that's the question that we will now try to understand, the way it's explained in these papers. However, I'm not going to be reading. I don't understand everything in the paper myself. These are really very, very mathematical explanations for this process. But I'll use a famous analogy to sort of try and explain to you. This came about, I think, initially because Margaret Thatcher, Prime Minister of England at that time, wanted to understand this mechanism and issued a challenge to her science minister to try and get her to be able to understand it, who then issued it to the physicists in the country, and ultimately they had a competition, and a professor from UCL London came up with a set of cartoons to sort of try and explain this, which sort of since then became famous. So I think in the original picture they have Margaret Thatcher there. I have a later version that I got hold of. So imagine there is a room of people. They're, I think they were supposed to be political party workers in the original cartoon. We say, they're having a party, whatever. Now, you have a famous person who shows his head through the door there. And in this picture is Albert Einstein. I've even seen at some point a picture with Barack Obama, the same cartoon. I couldn't find it. I was trying to hunt it down again, but I couldn't. But yes, so there are various versions. Margaret Thatcher, Albert Einstein, Barack Obama. But you get the picture, somebody very famous. Now, what will happen if, say, we had, Barack Obama walk in here now, and say he's trying to head to the other end of the room there because there's food there. Now, as he comes in, what's going to happen? What are you going to do? Are you just going to sit there? Yes. What you're going to do is you're going to and then try to go near him to perhaps talk to him. What are you doing here? Why are you here? And you're going to just, start talking to him. With the result, he's trying to get to the food there. Do you think he can get to the food very quickly? No, because you're going to stop him. You're going to make him want to talk to him, and he is unable to go to the other end of the room. Now, imagine a completely random person from the road walked. Now, Barack Obama is out of the picture now. Now we have another scenario. A completely random person walks in and again wants to get to the food. Is there going to be any reaction from you? No. The person is just going to sail through and get to the room, get to the other end of the room. So they'll move very quickly, almost as if they are massless or very little mass. They're moving very quickly. On the other hand, Barack Obama and his interaction with you means that he is slowed down. Heavy objects are slowed down. And he, by his interaction with you, appears to acquire mass and get slowed down, where somebody who doesn't interact with you whizzes through, almost massless, very fast. So that's the basic idea here. So you see it in pictures now. Albert Einstein coming in. He's surrounded by the people. He can't get to the other end of the room. And he is slowed down. He's becoming more massive. So that's the idea, that there is this field. We physicists call it a field. This field exists. And how much you interact with this field determines what kind of mass you have. If you interact a lot, you have a higher mass. If you interact very little, you have little mass. So the top quark interacts a lot with this field. That makes it heavy, whereas the electron does not interact much with this field at all, and therefore is very light. So that's the basic principle. Now, field is a mathematical thing. You can't really see a field. So how on earth are experimentalists ever going to prove that this theory is correct? This is what's happening, because you can't really see the field. And so part of the theory was that together with this field, there would be a particle that would be associated with the field. And if you discover this particle, then you proved that the theory was correct. Okay? And this idea is what is sort of shown here. That is, we go back to our party of people. Somebody just puts his head through there and says, oh, Barack Obama is coming down the corridor, or he's going to be here soon. So even though Barack Obama is not here, the fact that he's going to be coming here will have all of you starting to talk. Why on earth is he here, etc. And you start talking amongst yourself. This field here, this room, sort of there is an excitation in this room, this field. And this sort of a cluster that ends up being formed associated with this field is what we call the Higgs boson, the particle that you have heard about that we discovered. So it's this Higgs boson, which is sort of associated with this, physical field, which is responsible. The field is the one that's responsible for the mass, meaning the interaction with the field is what gives particles mass. The Higgs boson is just associated with this field. So when you find the Higgs boson, you prove that this field must therefore exist for this theory to work out, because all of this was what was given in those 3 papers that I talked about, where they predicted back in 1964 that there must be this esoteric Higgs boson particle which is associated with this field, and that is what's responsible for giving particles mass. So as you can imagine, that was the big search that went on in the last 50 years. So this is another way. Imagine a field that permeates the entire universe. Every particle feels this field, but is affected in different amounts. The more a particle interacts with this invisible field, as I said, it's not really something you see, the more mass it gets. And I think I already told you, but if this field is invisible, how can we prove that it exists? And we're helped because the theory predicts that the field has an associated particle, and this associated particle is the Higgs boson. And so what we try to do in our experiments is to create the Higgs boson, such that we can then see what happens, and we prove that the Higgs boson exists, and therefore there must be a Higgs field, and therefore we understand how particles get mass. So that's the big the discovery that you might have heard about a couple of years ago. However, and this goes back to something we had alluded earlier, that is, if we go back to our analogy where we had our helicopters colliding, and you remember the dinosaurs that came out, and I told you, so we'll try to do this. The accelerator energy you can think of is again at the very, very high end, perhaps more. We produce these dinosaurs, but the dinosaurs actually decay, or they are again broken down into they are short-lived. They don't live for long, and they are broken down into smaller particles. And this is actually the basic, I would say the challenge in our experiments is that we can create a Higgs boson, but it's not like we can actually just identify the Higgs boson, because we are never going to be able to find the Higgs boson as such. What we see is that the Higgs boson will be created, and it will then in turn, just like the dinosaurs, the Higgs boson is a dinosaur in this case, it will then decay to other particles. What we find in our detectors are these other particles. Using information about these other particles, we can figure out where they came from. Did they come from a Higgs boson? Did they come from somewhere else? And that is how we discover particles, by not necessarily finding the particle itself, but by seeing what it decays to and then finding the particles that it decays to. But that makes it more challenging, because it's not like there's this huge Higgs boson lying there waiting for you to find it. The Higgs boson disintegrates almost instantaneously, and you have to do a lot more work to figure out whether or not it was created. So it's like, what I think of it is like being a detective. You have, say, a murder that happens, you have a lot of clues, right? And you use all of those clues to reconstruct who the murderer was and how the murder happened. So what we see in our detector are all of these clues, and we put the clues together to figure out which particle they came from, the murderer, the particle, dinosaur, whatever. So the way we do this is, firstly, to some extent, we rely on theory, or various kinds of theories, which says, the theories came about associated with the Higgs, said that the Higgs has to decay in certain ways, meaning it will decay into 4 muons, it will decay into 4 electrons, it will decay into 2 photons. So in our detector, we try and look for these states, an event where there are 4 electrons, or an event where there are 4 muons. And then you go through lots and lots of this data, because what you can do is, and this is energy and conservation laws of physics, you can get the information about the energy and momentum of these muons. You can apply conservation of energy and momentum to figure out what was the mass of the particle they came from. And then you look through billions and billions of events to categorize and break them down into groups of these events, like 4 muon events. And then in each case, where did these 4 muon events came from? And if you get a large number of cases where these 4 muons came from a single particle which had a single a mass of, say, 100, then you know that you produced in your detector this particle which had a mass of about 100. I'm not using the units for a particular reason. A mass of about 100, and it decayed into 4 muons. But you need to see enough of this, because if you just saw 2, it could be from anything. So you really need to see a very nice, large number of such events to have confidence that you've actually gotten it right. And I'll talk more about this. I'll show you how we actually solve the Higgs in these cases. But that's what we do. So we analyze all of this data, and there's tons of it, to then figure out where they came from. Okay, so that takes me, so this is sort of the basis of, what it is that we are trying to search for, and how is it that we do it in reality. So for that, I take you to the Large Hadron Collider. So what we have there are proton beams moving in opposite directions, and they are moving in this circular collider, and they are made to collide at certain specific points. This is by using a special arrangement of magnets, which keeps them apart most of the time, and then brings them together at certain points. And at that point, we have detectors put in, such that the collision happens in the center of the detector, and you see everything that comes out of that collision point. Okay? Now, keep in mind that the proton, as I said, is not an elementary particle. So you have a composite particle composed of up and down quarks, and a composite particle composed of up and down quarks coming together. So in that interaction, you have the quarks in one interacting with the quarks in other. So there are lots of collisions happening, because they're not a single particle colliding, but because they are these constituent particles. They are colliding with each other as a result of this head-on collision. And to make things even more complicated, it's not like we send a single proton this way and a single proton this way. We send about, 1 billion protons this way and 1 billion protons this way, and they come together. So this is CERN. It's at the border of Switzerland, France. So you see the dashed line that's indicating 2 country boundaries. So part of the experiment is actually in France, and part of it is in Switzerland. It's near Geneva. We had a first run, which started in 2010, went on till 2011, where we had proton beams with what we call 3.5 trillion electron volts. This is a unit that particle physicists use. You can convert it into joules, which is what most of you are familiar with. Moving for a total collision energy at that point of what we call 7 TeV, or 7 trillion electron volts. Then they updated the accelerator the following year in 2012, such that the proton beams then came with 4 TeV, with the collision energy being 8 TeV. And what has recently started, and I'll come to this at the very end, is a new run, which is at almost double the energy of the previous run. So this is essentially the Large Hadron Collider. What it is, and some of its, the sheer enormity of it, is firstly, it's what you'd say almost the fastest, racetrack on the planet. And these are just aerial pictures. I've already told you the 2 different countries. But you have essentially several thousand billion protons, which are traveling at very much close to the speed of light. And this is, 16.8 mile ring over, and this is happening about, 11K times a second. So each of these collisions that I talked to you about having the detector is happening about 40 million times per second inside the detector. Very, 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 very quickly. I can't just even simulate that. And this particular speed, in case you're wondering what this is, in our real world speeds, it's that in miles per hour. So this is literally protons moving at, close to the speed of light, and very much so the fastest racetrack. Of course, in order to be able to do that, this is really a technological marvel in that sense. You need to create conditions which allow you to accelerate protons, because what will happen is you produce a very high energetic beam, but if there are other particles, it goes through what's called like a beam pipe, And if there are lots of other particles in this beam pipe, these protons will interact with these particles and lose energy. So you want to have this beam pipe kept in the nicest vacuum possible, such that you can preserve the energy of the proton beam, such that you can have these high energetic collisions. So essentially what we have is a vacuum that's similar literally to outer space, and the pressure as well is such that it is about 10 times lower than on the moon. So the technology which allows this to happen is therefore quite amazing. So you have these protons that you want to make them go around in a circular path like this. And you do this with the use of magnets. And what magnets allow you to do is, if there is a particle of a certain charge, then with the field, or the magnetic field of the magnet, you can make it go in a certain direction. So if it's a positively charged particle, it will bend in a certain direction. So if you have another positively charged particle, it will also bend in the same direction. But you can't have them both in the same, because then they will interact with each other, and then you'll have collisions everywhere. So you keep the beam pipe separate, except at the collision point where you have an opening, and then they come together, and that's where the collision happens. Okay, so the other thing is, in order for all of this to happen, they use firstly thousands of magnets, and to be able to be pushing these protons to this kind of speed, they again need to be using the latest of technology, which means that they work under extremely low temperatures, because under these low temperatures, magnets become what are called superconductors, meaning they don't have any resistance to the flow of current. They can allow large amounts of current to go through. Large amounts of current means large magnetic field. Large magnetic field means you can do nice bending. And therefore, you want to be able to have things which make this happen, and therefore, you need to have these superconductors work at extremely low temperatures, and that's why these low temperatures are needed. So when these two beams of protons collide in that tiny space that you have for a very, very tiny fraction of a second, the intensity is extremely high. And essentially, if you sort of measure it in terms of temperatures, that sort of amounts to temperatures like there's a billion times those at the heart of the sun. So extremely, extremely intense. And then, of course, around this collision point, as I mentioned, what you have is the detector that is situated. So the beam pipe is going through this tiny center in the middle of the detector. And that's where the interaction, this is an opened up detector. So this is my detector that I will talk about in a second. But it sort of completely surrounds the beam pipe, because you don't want the particles that are produced of the collision escaping. You want all of them contained in your detector. So the detector surrounds the beam pipe like that. And let's see, and yes, so it's recording all of these collisions every second. And you really need very precise detectors to be able to measure properties of things which are happening so quickly. So this is sort of a pictorial description of a typical particle physics detector. And things haven't changed. I mean, this picture is probably the last 40 years. The idea is the same. We're just using the latest in technology to give us better resolution and better precision. So a particle detector, typically we say, is like an onion. It has layers, okay? Just like an onion has layers. So we are now looking at sort of, starting from the insidemost or the innermost part here. What we do is we want to detect different kinds of particles that I've talked about: electrons, muons, photons, various hadrons. So we built not one detector, but actually different detectors, each of which is going for a particular kind of particle. Okay? So we build a detector which is primarily aimed at measuring properties of muons, for example. Okay? Then we build a detector which is primarily aimed at measuring properties of particles which we say interact via the electromagnetic force or interaction. Because if it interacts using the same kind of force, we believe that its way of interacting is the same, and therefore, with the same kind of idea behind the detector, we shall be able to figure it out. So that breaks brings it down into these categories that I have broadly put here. First is the innermost layer is what we call the tracking detector. This is typically using silicon technology. The semiconductor industry as we know it today came out of the needs of particle physics experiments, essentially, because they wanted to build these extremely precise, what we call tracking detectors to detect these particles, and that advance led to where it is today. So this is like a track is thinking of, imagine a person, walking in the snow or skis on the snow. You leave a track, and essentially that's the kind of particle will leave a track as it goes through this silicon detector. It is, there are processes called ionization. There are these detectors which are filled with gas. A particle goes through it. It ionizes it. It makes it mark at certain points. And you have electronics which is attached to it to get these signals to figure out where in this detector this particle hit. And using this information about the various hits, a hit here, hit here, hit here, you can literally fit a track through it. And so we have various algorithms which allow us to fit a track through it. Now, only charged particles will leave a track through such a device. That's how they are built. A neutral particle does not interact in the same way through this ionization method that I talked about, leaving these hits. So already, using the tracking detector, we can differentiate between a neutral particle and a charged particle, because a charged particle will leave tracks, a neutral particle will not. The other wonderful thing about the tracking detector is, and this is, anybody who's done or will do magnetism, and this is, anything you do in your high school electricity and magnetism is really how you build these detectors. A charged particle going through a magnetic field bends. It tries to follow a circular path. Depending on the charge of the particle, whether it's plus the electron charge or if it's negative, it will bend, meaning if the positively charged particle bends like this, the negatively charged particle will bend like that. So we will look in our detector to see how these tracks are. If the tracks are like this or if the tracks are like that, with that we can tell whether it is an E plus or it's an E minus. It's an electron or a positron, because it's bent this way or it has bent that way. So you've identified that it is charged. You've identified what its charge is, positive or negative. The other thing you can identify is its momentum. Depending on the momentum of the particle, it will determine how much it bends. If it is a low momentum particle, it will bend like this. If it's a high momentum particle, it's going to bend in a huge circle. Okay? So if a particle is bending with a large, what we call radius of curvature, it typically means it's a high momentum particle. If it has a small radius of curvature, it's a low momentum particle. And using our knowledge of magnetism and what this radius of curvature is, the magnetic field, which we know because we put in the magnets, we can actually figure out what the momentum of the particle is. So we figured out the charge, we figured out the momentum, and whether or not it's neutral. And all of this can be done in this innermost layer called the tracking detector. Okay? And so you can look now, for example, the top two lines, or photons, which are neutral, and electrons and positrons. I haven't shown the bending here. It's difficult to sort of show it in this picture. But the photons leave nothing in the tracker, so that means they are neutral. And the electrons and positrons leave a track. Okay? Then what you have is the next detector surrounding it. Because as you see, I can go down further. I see muons. Muons also leave a track. I have charged hadrons, so protons, for example, they also leave a track. Neutral hadrons don't, neutrinos don't. So now, how on earth will I differentiate between electrons, positrons, muons, and charged hadrons using just the tracker? I can't, because they're all charged, and they're all leaving tracks. I can figure out that this has this momentum, but it doesn't tell me whether it's a proton or whether it's an electron or it's a muon. I need something else to be able to pinpoint it further down into whether it's an electron or a muon. So I need another detector. So I construct then a detector which is called the electromagnetic calorimeter. This essentially uses the fact that certain particles, such as electrons and photons, interact via the electromagnetic interaction, and what that means in real life applications is if you have certain kinds of material, the electron will come and it will just stop there because it just interacts, it loses all of its energy in there. So you can design a detector whereby the electrons and photons will stop there, and then you can measure all of the energy that it deposits when it comes to a stop. And so now you can, using the top two, the tracking detector and the electromagnetic. So the lines that you see here with they're called like showers because it sort of showers energy and comes to a stop. Using two detectors, the tracking detector and the electromagnetic calorimeter, you can differentiate between photons and electrons and positrons because the photon does not have a track. So if you have something which has a shower of energy in the electromagnetic calorimeter but does not have a track in the tracking detector, you've got a photon. But if you have something which has a shower of energy in the electromagnetic calorimeter and also has a track in the tracking detector, then it's either an electron or a positron. And then you look at which way it's bending to figure out, is it an electron or is it this positive particle, the positron? So you can, using these two detectors, distinguish between the first two sets. Now, muons are very special particles in the sense that they leave a track through the tracking detector. They don't interact with the detectors that you see after that. And what you have at the end is a special detector that's put in to measure the properties of the muon. And in these, it does it in similar ways by looking at momentum and charge. So anything that goes through and is only caught by the detector at the very end is therefore a muon. And then we have a special kind of, the basic principle is the same, a hadronic calorimeter, which essentially will measure the energy of the hadrons, because these hadrons will not interact via the electromagnetic interaction. So they will not leave any energy deposition in the electromagnetic calorimeter. They will go straight to the hadronic calorimeter and leave their energy there. So now, putting all of this together, you can then start to distinguish between all of these different particles. So you need all of these sort of sub-detectors to make up the full detector to be able to figure out what you had and what its momentum was and what its energy was. And then there is a very special category of particles called the neutrinos, which actually interact very little with our detector and essentially go unnoticed and unescaped. And the only way we detect their presence is, for every physics process has to sort of follow conservation of energy and momentum. And when we find that this is not coming out to be true, meaning we've measured the energy and momentum of the outgoing particles, and we don't quite see the conservation coming up, the missing part of it, we say, is attributed to this neutrino. There must have been a neutrino that was produced, and it went away with this missing momentum. So that's the complication. So I should go a little quickly through the rest. So I think the thing I wanted to point out is there are actually not one, but there are four big detectors: ATLAS, ALICE, CMS, and LHCb. I'm going to just quickly go through CMS, which stands for Compact Muon Solenoid that you heard from Yvonne. Compact is not small. It really is a relative term. CMS is compact in comparison to the other detector, ATLAS, which is larger and less dense, whereas CMS is smaller and more dense. It's huge. It's about 15 meters wide and 21.5 meters long. It weighs twice as much as the Eiffel Tower. It has the most powerful magnet of its kind built ever. And I think these pictures usually have a person somewhere to denote, but I think I had another picture to sort of show how it is. And it's taking, these collisions are happening very, very quickly, and it's taking pictures, just as you can imagine, a 75 megapixel 3D camera would do. And all of it was assembled all over the world in different components and then brought together at CERN, and they're now lowering it through a hole through the top, and the detector is sort of, you see this hole here. It's being lowered. This process took over 10 hours. And it's getting down here. Now you see it arriving. And this is just part. And this is the whole thing coming together. And in the final few minutes, I think I'll just mention that if all of this was not challenging enough, we talked about the large rate of these collisions, meaning they're happening 40 million times a second. That's what I call the bunch crossing rate there. How much we are saving for analysis later is of the order of a few hundred events per second. So we have 40 million events happening per second, and we are only saving about a few hundred per second. So we need to have a mechanism to be able to do that, because the rates of the processes we are looking at, like for example the Higgs, are extremely small. And we want to make sure that in the few events that we save, we're actually saving the interesting ones, and we are not throwing them away, because these decisions that you make online are really for good, meaning you keep it looking later, or you throw it away. So you really don't want to be discarding your Higgs and your new physics events in that fashion. And that's what I call the trigger, which is the work that Yvonne alluded to, which is part of what I do, and I'm happy to talk more about it later. But also to give you an idea of, even at this sort of few hundred events per second, the amount of LHC data in 1 year goes up above where the Concorde flies. So that's if they were put in tapes or disks that you stacked on top of each other. That's how it would go. So you would have to go through all of this to actually get to your few interesting events that you want to see. So this is literally looking for a needle in a haystack. Despite all of these difficulties, we found the Higgs, and I think we talked about how we, I think I have it here. We look at all of these different events which have a certain mass, and we found that we got a lot of events which had a certain mass, which is that little peak that you see there. And that constituted the Higgs decaying into 2 photons, a particular kind of Higgs decay. Similarly, there was another kind of decay where it decays into 4 muons or 4 electrons. So we did that analysis too, and then we see these are independent analyses. That gives you a mass of about 125, and this other analysis, completely independent, using different final objects, gives you again a similar mass of 125. So this gives you confidence that you can do completely different analyses which make use of different parts of your subdetector and find the same particle, which according to the theory was supposed to decay in these 2 different ways. And not just that, this was what my experiment found. Our competing experiment Atlas, also at CERN, exactly the same thing, completely independent. We don't share our results or discuss it until we get to the point of making a public announcement. And then we find it was exactly at the same point. So that gives everybody confidence, which is why this ended up actually in the Nobel Prize for the sort of the main surviving people from the theorists. Our collaborations have 3,000 people. You can't really do anything, but they got it after the Higgs was discovered and not before that. And then finally, I just want to say that this run discovered the Higgs. However, the story is not complete, because we need to look at it from every angle. Firstly, is this Higgs exactly the same Higgs that was predicted, or is it very different? Or is it similar but not quite the same? And you need to do that by looking at every angle. And I like this picture because somebody is just looking in a very tiny space. They think they're holding a rope. This one thinks they're holding a spear. This one has a wall. But then you look that no, they're all actually parts of something completely different. Okay. And so you need to see the whole picture, and that is part of what we are doing at the LHC in this run, where we are trying to answer some of these questions. And one of them was this big question of, I told you, matter and antimatter. At the start of the Big Bang, they were supposed to collide, lead to an explosion, and we were all supposed to disappear. But we live, and therefore, where has all the antimatter gone? I don't know the answer. None of us know the answer, and we are trying to find that. And then I think, so that's, I think, a big question. I think one of the big theories that helps to explain this, which a lot of us are searching for, is what's called supersymmetry, which says that for every standard model particle that you see on the left, there is its partner particle, which is what is given on the right-hand side. Every name, you add an S to it, it becomes a supersymmetric particle. And so what we are trying to do is search for these supersymmetric particles. So just as we found the Higgs and that proved that the Higgs theory was correct, similarly, if we find any of these particles, that will prove that the supersymmetry is correct. This is the LHC restart in 2015. This is at 13 trillion electron volts. The first runs were at 7 and 8. So it is really a big jump. And more energy means we can produce more massive dinosaurs, more massive particles, which will decay in more interesting ways that we will then try. And one of my favorites, because this is actually a real event that we got, which has everybody very excited, is an event which essentially shows 2 electrons. And in the standard model, there is this particle that I talked about, the Z boson, which decays into an electron and a positron. And what we have are new physics theories which predict that there is a partner to the Z boson. And out of any particular imagination, we call it the Z prime, Z and Z prime. And the Z prime decays in the similar ways to the Z boson, except that it is much more massive, and that's why nobody has seen it yet. But the increased energy at the LHC will allow us to therefore see it. And so we had an amazing event which was at 3 trillion electron volts. We've never seen any object that heavy massive. And this was indeed, whatever it was produced. It decayed into an electron and a positron. And, but it's just an event. So at this point, you really can't say anything. But if, by the end of next year, we see 100 of these, and all of them are at 2.9 or 3-ish TeV, then we've got your new particle. So that's our hope, that we have discoveries awaiting us next year. And I think it's clear from all the various open questions I told you about matter, antimatter. We don't really understand a lot of the standard model. And perhaps there is a new standard model that's about to happen. And maybe in a few years, we'll have a new discovery awaiting us. So stay tuned.